It is controversial in some ways. There is this the duality business between is a photon a particle or a wave, and I know my good friend Walt Thornhill says it's a wave. Don't argue with me. I'm really not that expert in that because the areas of electrical engineering that I was in really didn't involve quantum mechanics. Although I think there's a lot of good things about the quantum mechanics, and I think they can solve a great number of very important problems. The reason I have my doubts about it is that Wall has said to me that there are places in quantum mechanics where the principle of causality is not recognized or it doesn't apply somehow. Whereas in all the rest of engineering, the engineering that I know, you do something and you get a reaction. Something happens. You cause something to happen. That's causality. Well, in quantum mechanics, something just happens, and these two electrons are interangled, and it gets a little bit for me on the hocus pocus side, and that's the reason I never got into it. So all I can say is I'm ignorant on that. Oh, it's all the same thing. Well, I referred to Maxwell's equations before, and the two major, well, we're talking about this action at a distance. So one of the things, as I said, you can postulate the existence of an electric field. Now that doesn't mean there really is an electric field in there. I remember when I used to teach, I would draw electric field patterns on the blackboard, and I always used red, I think it was, for electric field and blue for magnetic fields, because they're two very different things. And one student asked me one day, he said, are electric fields really red? I said, oh God, no, John. They don't have any color. They are postulates that seem to work. And when I say seem to work, they have worked every single time anybody has ever used them properly. Now, I've heard some people say, well, I've disproved Maxwell's equations. No, you haven't. You just didn't apply it properly. It's any principle in science has a range of applicability. And if you go outside of that, it's useless. And a prime example is inside an atom. There's special kinds of forces between the nucleus of the atom and the electrons that go around the outside. And if you try to apply Newton's equations, I'm just talking about Newton, F equals ma, the basic, why did the apple fall kind of thing. Inside of an atom, it won't work. So Newton's laws, Newtonian mechanics, Clark, Maxwell's equations, they all have areas, regions in which they work. The one thing I will say, it seems as though the electrical force, the electric force and the magnetic force, two very different forces, seem to extend over a wider range of applicability than some other forces. And I may get an argument from somebody who hears me say that, but I think that's true. I think it's provable. But you asked, what's the difference between an electrical and magnetic force? And the magnetic force is a force between particles, or I shouldn't say particles, between charges. If those charges happen to be on particles, like an electron and a proton, yes, they're between particles. The magnetic field, if you will, has to do with when you get a bunch of charges moving, like those charges moving down the wire. If you put your thumb in the direction of the current flow, the electrons are really going the other way, we know. But if in the direction of the assumed current flow, positive charge flow, then your fingers will go around and that'll show you how the magnetic field is wrapped around that wire. And well, what's a magnetic field? Well, if you do have another wire over here and this wire over here, then you can analyze those two magnetic fields interacting. And I don't know whether I should, maybe you may want to cut this, but space is what's called a linear vector space. And magnetic fields add up like vectors. If you have one vector here and one vector here, you can say, well, that's the resulting vector. You can add up vectors, and those magnetic fields, multiple magnetic fields, when you put them together in free space or in air, they can be added together to get the total magnetic field. And then if you take a wire and cut it through there, when you move a conductor through a, quote, magnetic field, you produce a current. And you can certainly measure that current. Somebody might say, well, is the magnetic field really there? Well, it's postulated to be there, and if you use it like it as if it were, you get the right answer. So both electric fields and magnetic fields are postulated entities in three-dimensional space. We consider them to be real, although you can't touch them, smell them, or kick them down the road. They're there because we know if you use them properly, you get the right answer every single time. Oh, that's easy. Plasma is ionized gas. Now, what's ionized gas? Well, you know what gas is. Gas is when the molecules of a substance are not so clamped together that each one can pretty much go on its own, depending on whether you blow on it or whatever. There's solid, liquid, and gas. And then there's the fourth state of matter is plasma. So solids are like the wire. The molecules are linked together in a matrix, a chemical matrix that the chemists can tell you exactly why they can't move. And that's why positive charges don't go in a wire. The wire is solid and it doesn't move around. But once in a while, an electron pops off of one of those atoms in those molecules, and it does move through the wire. Liquid, you know what that is. I mean, that's water. Okay, so the molecules are still attached, but they're not as firmly attached as they are in the solid state. Gas, well, they're free. Now, gas is made up of molecules, free floating molecules, which contain either one or more or several atoms. And those atoms, each one of them, has a certain number of positive charges in the nucleus, in its nucleus, and an equal number of electrons around the outside. So an atom is electrically neutral. Same amount of the total. It's 14 protons in the nucleus. It's going to have 14 electrons in its orbits around that nucleus, and therefore the sum of the two is zero, so that it's electrically neutral. It won't. You can hold a charged plate and it's not going to move. The final step on that one is there's solids, liquids, gases, and if you take a gas and pop one of those electrons in any one of those atoms loose, it's a naked negative charge, and because it left the atom that was its home atom, that atom has the same amount of plus charges as it always did, but it's got one fewer negative charges because you just let one go. So what you've ended up doing is it's so-called ionized that atom by removing one of its outer electrons from one of those outer shells. And what you've done is created a pair of oppositely charged but equal valued charges. A plasma is a collection of those things. And it turns out, because of experimental work that's been done over the last 100 years, that if you take a cloud of gas and ionize, that is, pop loose electrons from as little as 10% of the atoms in there, that region will act completely as an electrical body and will not really respond if you act on it electrically. It won't respond to gravity or any other Newtonian physics. So all it needs is 10% ionization. If you 100% ionizes, wow, that's fantastic. But it's fairly easy to ionize a gas, and you heat it up, or you put an electric field in it, and you pop loose one of those electrons. So that's what a plasma is. It's ionized gas. Yes, as far as we know. And the other night, my buddy Jim Ryder said, forget that 99%. It's 99.99%. So, sounds good. Just that electricity is important. Don't ignore it. We can explain things by using electrical laws like Maxwell's equations and Lorentz equations and stuff like that. That seems inexplicable by just if you confine yourself to Newtonian physics and forget about the fact that things can get charged or they can become ionized. There was in my talk, I ended it up with a slide shows a fellow that I've met, and he's actually been here to the EU. One time he was an astronomer, and he sat through a bunch of our lectures, me and Wall and a few of the other guys. And at the end of it all, he says, yes, we know there is electricity in space, but it doesn't do anything. Yes, it does.